Okay. So second course of probability and statistics. So I have finished the previous session with something like this, in particular definition, the first definition here, okay, concerning independence. So remind that during the previous session, we have done some exercises, okay, to begin with, but I have introduced the real definition of what is a probability after reminding you what is an intuitive notion of probability. So this is this definition, okay? Probability of the universe is 1, and what we call the sigma additivity property that we are going to handle today, okay? I say to you, don't worry, even the definition seems to be theoretical because the thing that you used to do with intuitive notion of probability are also okay in this framework, fortunately, okay? So we have all these kind of properties that are still true in the framework of my preceding definition, okay? One consequence of the sigma additivity is the fact that you can, in some interesting situation, compute the probability of some special sets as limits, something that may be comfortable to do, and it's really a consequence. So you have the proof of this theorem, okay, on my website in the list of proof number 1 associated to this course, okay? I don't have the time to do it in class, okay, but you have it if you are interested. It's not that complicated, okay, but I have a small board, I don't have that time to do this, okay, so I prefer not to do. So we are going to see just after a little exercise using this property, okay, to do the question number 2. Then we have seen the definition of independence, okay? So for the definition of independence, in the case of two sets, no problem. A set A is independent from another set B, okay, if the probability of the intersection is equal to the product of the probability. It's what we mean by independence, okay, in the case of probability, okay? The second point of the definition is a generalization to more than two sets, okay? So, you have this statement here, and in order to make this statement clearer, okay, I have said to you what happened in the case of 3 sets, okay? So I remind this, when you have 3 sets, we say that 3 sets are independent if, in fact, we have several conditions. Independence for 3 sets doesn't mean they are independent 2 by 2, something that is stronger than this. So we have the independence 2 by 2, that is P of A1 intersected with A2 has to be equal to the product, okay? The same for A1 intersected with A3. And for the last, A2 intersected with A3. But this is not enough. Okay, I add in the definition the fact that if I take the intersection of all of them, the probability of the intersection of all of them has to be equal to the product of the associated probability. Okay? And if you have 4 sets, you do this 2 by 2, 3 by 3, and 4 by 3, and so on. Okay? So it means that if you have a big number of sets to prove independence, may be a little bit complicated. Okay? If I use basically this definition. Okay? Let's see a little exercise from one of the lists, okay, concerning the fact that you may have these 3 and not this one. So it means that when you have to prove independence, you really need to prove. Just up. Okay. So let's do this exercise. So this exercise is taken from the list 3 of exercise, what I have called in my web page TD3. Okay. So list 3. Let's do the not this one. Which one? The 5. Exercise 5 of the list 3. It's just something to underline that when you have to prove the independence of 3 sets, be careful, because if you prove only this one, it is not enough. Okay? So let's have a look on the statement. So we flip a fair coin twice. Okay? Twice. And a priori, I have no relation between the first and the second toss. Okay? Let us consider that I have the three following events. A1, I obtain head on the first, A2, I obtain head on the second, and A3, head on exactly one. Okay? And I want to prove that they are pairwise independent, meaning that these three are okay, but not independent, that is, the last one doesn't occur. Okay? We have to compute probabilities. Okay? So in this basic situation, in fact, I can use what I have called the intuitive notion of probability because I have to count here. Okay, I am in a situation where to compute probability, I have to count. What is my universe here? So I flip a coin 2 times. Okay? And here order is important because we speak about the first and the second one. Okay? So in my universe, I have how many elements? What are the possible outcomes in this situation? I have 4 possible outcomes. Head, 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 tail, tail, head, tail, tail. Okay? So in my universe, I have these 4 elements. Okay? I have pairs representing that the first component is what happened in the first toss, and the second what happened in the second one. Okay? And the number of elements in omega is 4. Okay? So to compute probability, I will divide by 4. Okay? So what is A1 and what is the number of elements in A1? So what is A1? Head on the first. And for the second, no condition. Head on the first is this one and this one. Okay, so I write it for the first, okay, and I will use for the other. So I have this one. And how many? 2. So when I compute the probability of A1, it is 2 over 4. That is, of course, 1/2. Okay, so be on time at 9. Okay, it starts at 9. I will repeat this, okay, during the first months in general, okay, start at 9, and one time I close the door, okay, at 9, and after it's okay. So this one. So for A2 it's exactly the same. Head on the second, it means that I have this one and this one, so I have 2 elements in A2. So the probability of A2 is equal to 1/2. What is the probability of A3? So A3 means head on exactly 1. So exactly 1, that means this one or this one. So once again, I have 2 elements in A3. Okay? So the probability of all of them is equal to 1/2. Okay? And I will use this in order to compute these terms here. Okay? What is A1 intersected with A2? What is A2 intersected with A3? And what is A1 intersected with A3? So if I am in A1 in A2, it means that head on the first, head on the second, head on both. So I have a single element here that is head, head, okay? And so the probability of A1 intersected with A2 is equal to 1/4 because I have only one element in the intersection. Okay? I can try, but I have a small board. So there is let's say, a dilemma. If I write in a bigger way, I will erase the board very often. You can see here? Yeah, because I have a really, really small board. Okay? I will try to do a little bit better. I see perfectly, you know. And you are young. Yeah, but I will try to do my best. Okay? I will try to do yeah, but I speak also, huh? Okay, but I will try to do my best. Okay, so I try to improve a little, okay, and try to be more focused on the board. Okay, I hope that it will be okay. A1, A2, A2, A3, A1, A3. Okay? So are you okay that the probability of A1 intersected with A2 is equal to 1 over 4? So what I have in A2 intersected with A3? 1, add on the second, and add on exactly 1. Okay? So I have add on the second and add on exactly 1, so it means that it is take add. I don't have the choice. Okay? And so the probability of A2 intersected with A3 is equal once again to 1 over 4. Okay? And for the last, add on the first and exactly 1, okay? It means that it is this one, add tail. And once again, the probability of A1 intersected with A3 is equal to 1 over 4. So what I see when I have done this computation, I see that all these relations are okay. Because P of A1 intersected with A2 is equal to 1 over 4, that is equal to 1/2 multiplied by 1/2. Okay? So it means that this one, and this one are okay. So I can say that they are independent 2 by 2. Okay? So to see that they are not independent, I have just to check that this one is not fulfilled. This one is not fulfilled. So to prove that this one is not fulfilled, okay, I am interested in this one. And what is this set? Empty. Is it clear for everybody that it is the empty set? Well, A1, it's add on the first, A2, add on the second, and A3, add on exactly 1. It's not possible to have add on the first and on the second and n exactly 1. Okay, so empty set. So the probability of this set is what? 0. Okay, and I can't have this one because 0 is not equal to 1/2 times 1/2 times 1/2. So I don't have this one. Okay? So you have here an example where you may be pairwise disjoint, but not, pairwise independent, but not independent in the sense of the definition. Okay? So it was just to illustrate the little definition. So be careful when you have several sets. If you have to prove independence, you have to do all these things, not to focus only on pairwise independence, because it's not the same thing. Okay? So let's come back to my slides. So do you have some question on this? Yeah?
So they are independent but not. They are
I have the noise. Okay, I have, so you have to speak up.
So they are independent but not pairwise independent.
No, it's the converse.
Okay.
They are pairwise independent, okay, because all these three are okay, and they are not independent because the last one is not okay. Yeah. So you do. So what you do if you have 4 sets, something that I have already said, you have to consider the case 2 by 2, the case 3 by 3, in the case the last one, the 4 at the same time. Yeah, but the sets, but you have here 2 by 2 and 3 by 3, you have 4 by 4, and so on. So it means that really if you have a big number of sets, it's something that is, if you use basically the definition, okay, you have a lot of things to do, in fact. Okay? I have this one. So if you have some question, you ask me, I prefer, please, excuse me, ask me. It's my job. I am paid. Don't worry, okay, you can ask. And I think that, I hope that I will give you a better answer. I hope. So I can erase this, okay? Okay. So I have my definition of independence for two or more sets, okay? And just a little proposition here. Just a little proposition. You see the slides here? Because for the board, okay, I will try to work big and to write bigger, but is it okay for you? Because I have lights here. No? You see nothing with this one. I think that it's worse than my board. I don't know if it's possible to do something. Yeah. Typically, maybe it's something that the first that enters the room in the morning can try to do by itself, okay? Because I think that the quality would be better if we have less. Or maybe I can also switch off the light if you prefer. For me, it doesn't. I can do this. It's better for you or not, as you prefer. You prefer light or not? No light? Prefer this way? Okay. But tell me, huh? If you don't tell me, if you don't have questions, it's not possible for me to know and to answer. Huh? Okay, so it's better like this. So a little proposition. What is the meaning of this proposition? Well, it means that my hypothesis here is that A and B are independent. And I say that if it is the case, if A and B are independent, directly, without supposing anything more, I have the fact that A complementary and B are independent, that A and B complementary are independent, and that A complementary and B complementary are independent. Okay? Without extra hypothesis. The only thing I need to know is the independence between A and B. And I have the independence in the other cases, okay? Directly. So I will do the proof of one, okay? And if you want to exercise at home, you can try to do exactly in the same way the proof of the two other statements, okay? The idea is exactly the same. So it's my proposition 5. So let's see the... So I repeat, I really, I don't want to focus on it, but you will see that I think that it's better to write like this. It's bigger, perfect for you. For the moment, I don't have done real computations that are computations that take me several boards. If I use a big writing, okay, for sure I will be, okay, it will be mandatory for me to erase more the table, okay, and it won't be possible for me to keep the formula more on the board, okay, so there is a price to pay for this, okay. So proof of the proposition 5. So my hypothesis in the statement is that A and B are independent. So P of A intersected with B is equal to P of A times P of B, by definition of independence. Okay? And what I want to prove is that A complementary and B are independent. So what I want to prove is that P of A complementary intersected with B, okay, is equal to P of A complementary times P of B. So I have my hypothesis, I know what I have to prove, okay, and now we are going to prove using the hypothesis, okay? An idea? So here, let's say that I am able to compute this probability through this formula, and I want to be able to compute the probability of this one here. Okay? And the idea is to try to find a kind of link between these two sets here. I can say the following. A and A complementary, okay, are two sets that are a partition of the universe. Something that I have defined in the prerequisite. And I will come back on this point, okay, in a few minutes, okay, in the chapter concerning conditional expectation. So what is a partition? In the case of two sets, I have that A and A complementary for sure are disjoint, and the union is equal to the whole universe. It means that you can separate in two parts, okay, that are with no overlap, okay, my universe omega. So if I do a little picture, you have omega here, and for example, I cut it in two parts, okay? And I have my set B here. My set B, that is something like this, let's say, okay? I don't know why is it, but let's say this situation. And in fact, what is interesting with the partition, it's something that we'll use another time today, is that in fact I can decompose my set B by using the element of my partition. I can say that B is equal to A intersected with B, disjoint union with A complementary intersected with A. And what is the meaning of this one? It just means that you see B, that you can separate in two parts. This one, that is A intersected with B, and this one, that is B intersected with A complementary. And if you do the union of the two, you recover the whole B, and the two parts are with an intersection equal to the empty set. Okay? So why I do this? I do this because since I have a disjoint union, I can use the basic rule of computation of the probability. The second point here, the probability of the union is equal to the sum of the probability. So I have P of B that is equal to P of A intersecting with B plus P of A complementary intersected with B. Okay? But I have one hypothesis. What is my hypothesis? The fact that this term is equal to P of A times P of B. And so I deduce from this one that what I am interested in, that is the probability of A complementary enter B, may be written as P of B minus P of A, P of B. And what can I do now? I can put, for example, P of B into factor, and I obtain 1 minus P of A. But what is the probability 1 minus P of A? If I have a look on this here, 1 minus P of A is equal to P of A complementary. And so you have done the job. From my hypothesis, you prove that the probability of A complementary intersected with B is equal to the product of the associated probabilities. So, by the definition, okay, you have the independence. By the definition, here, you have the independence, okay, of A complementary and B. And at home, okay, you can try to do by yourself exactly the same thing for the case A and B complementary, A complementary and B complementary, okay? And you will obtain exactly the same statement, okay? So I have this one. So if I remind, I ask you to do a little something at home, okay, for today. You remind? No? I ask you to try to do this one here by yourself. So when I ask you to try to do, try. It's possible, okay? It doesn't mean do it perfectly, but try to do to see what are your problems in fact. And when I will do the correction, it will be better for you, okay? It's the same for the tutorial. So you see that the tutorial will be with me, in fact, mixed in the course. Okay, I prefer to work like this. I do the exercise, okay, when they appear naturally in the course. Okay, I prefer like this. You have at the beginning of each list the exercise we are going to do together. So you can try to do them at home. Okay, so I repeat, to do them at home doesn't mean to do them perfectly, but to try to do, if possible, to know what are your problems, and then when I will do the correction, it will be more efficient this way. Okay? The classical way, huh? It's not typical to this course. Okay? So I have to do this one, but before to do this one, okay, just a little remark That is the end of this part of the slides here. So it's something that will be out of the scope of the course. When I mean out of the scope, it means that no for the exam. Okay, it is clearly written on the slides. Okay, but typically, okay, if you want to continue probabilities during the second semester in other courses, okay, it's something that you will have to deal with. So if you have time, have a look on. Okay, if you have too much difficulties in the beginning of the course, don't spend time on this part. Okay, it's 2 slides. Okay, but just to say the following. I have given to you the definition of a probability. Okay? I have said to you that a probability, if I am not in the intuitive case, a probability is what? Is a mapping from a set A, that was the set of definition, with values in 0, 1, because the probability is a number that is in between 0 and 1, okay? And that fulfills 2 hypotheses, okay? 2 hypotheses that are, I remind, that are what? P of the universe is 1, okay? And if I have a sequence of pairwise division sets, so for any sequence of pairwise division set, the probability of the union is equal to the sum of the probabilities. Okay? Definition of a probability. But in general, okay, when you define a mapping, the first thing you define is the set of definition. And at this stage, okay, I have said nothing about the set of definition. Nothing. So, in this course, it won't be a problem. Okay? So you won't have to ask yourself the question about what is this calligraphic A here. But I want to say a few words concerning this because, okay, in fact, it's a deep notion. So I have a probability and I just see it as a mapping from some 1 into 0, 1. Okay? If you have a look on the consequence of this definition, that is this one here, you have a lot of probabilities. Okay? You have P of empty set, you have P of A union B, you have P of A intersected with B, you have P of A complementary, and so on. But implicitly, when I write this, it means that all the sets involved in this proposition here belongs to my set of definition. Okay? Because I want to be able to compute effectively a P of empty set. Okay? So I take another basic example. If you have a mapping F from 0, 1 into R, if I ask you to compute F of 2, it's stupid. Because 2 is not in the set of definition. So a priori, when I have a mapping, I am not able to compute the image of everybody, just the one that are in the set of definition. A probability is a mapping, so I have exactly the same problem. Okay? But here, I said nothing about the fact that, okay, I suppose that A and B are in the domain, okay? So it means that I can compute P of A and P of B, and I have consequences, okay? Meaning that I can compute P of empty set, why? I can compute P of A union B, why? Is A union B in the set of definition? I don't know, because here, okay, if you have, I don't know, 1 plus 1 half, I do the sum, I am not in the domain, it's not that natural to have this kind of property. So just to say that, in fact, for A, I can't take anything I want. And I repeat that it won't be a problem for you in this course, but I just want to underline this point. And typically, if I come back to this one, I see that, okay, if I am able to compute the probability of A and the probability of B, that is A and B are in the set of definition, but I want to be able to compute this one, for example, or this one. So it means that A needs to have some structure. This structure is something we call, and it will be the last time I will pronounce this word in this course, it's what we call a sigma algebra. Okay? And what is a sigma algebra? So you have a definition with my explanation here, but the only thing I want you to focus on is that the sigma algebra will be something such that when you have the right to compute P of A and P of B, that is when you suppose that A and B are in the domain of definition, you will be able to compute the probability of the union, the probability of the intersection, the probability of the complementary set, the probability of omega, the probability of the empty set, and so on. Okay? And the definition of a sigma algebra, that is this definition, so without a number, because it is not in the scope of the course, okay? So I don't consider it as a definition in this course, but what will be a sigma algebra? But it will be a set of definition, so a set that contains subsets, okay? And fulfilling the fact that, okay, I am able to compute the probability of the empty set because the empty set is in the set of definition. I am able to compute the probability of omega because omega is in the set of definition. If I am able to compute the probability of A, I will be able to compute the probability of the complementary. If I have a sequence of sets for which I am able to compute the probability, I will be able to compute the probability of the union and the probability of the intersection. This way. Okay? So it was just not to make silence on these points, but I repeat that from now on, forget what I said. But you will see in the second semester that we won't be able to forget this. Okay? And typically, if you want to follow the course of statistics, probabilities, having in mind, for example, mathematical finance, it will be a notion that you will have to deal with, later on. Okay? But it's not the scope of my schools. Okay? So sigma algebra, one time, last time. Okay? I come back to what I asked you to do, that is this little exercise. Okay? It will be the way to discuss about the induction reasoning and to use this theorem here. So may I erase the board? So don't hesitate to ask questions. For the moment, I have no questions. So two possibilities. It's very easy. I don't think so. Maybe. I hope. Or, you understand nothing. I don't hope so. Okay? So ask and ask questions. It's your job. Typically, because I don't know what will happen in 1 week. Maybe, it's the last time we see together, concretely. Okay? Possible, I don't know. Okay? So I am here. Okay? Ask questions. It's important. Okay, so it's the little exercise at the end of the slide number 4, concerning the definition of a probability. And I have two things to prove. So my statement is the following one. I have a sequence in the set of definition of my probability. Okay? And I want you to show first that for all n belongs to n, the probability of the union, so I just take the same notation, so union from I equal to 0 to n of the AI is less than the sum of the probability. And it will be just a consequence of the definition of a probability. And I remind you the definition of a probability. A priori, the only thing that I am able to compute with this definition basically is the fact that when I have a sequence of pairwise disjoint set, the probability of the union is equal to the sum of the probabilities. Be careful because here I have a big hypothesis that they are pairwise disjoint. I don't do this hypothesis here. I have an arbitrary sequence here. So I don't know if they are pairwise disjoint or not, and in general they are not. Okay? So you can say that, I have the equality here, so of course I have the inequality. No, it doesn't work like this because here you have an extra hypothesis that you don't have in this statement here. Okay? Okay. So I have to prove this. So in the slides concerning prerequisite, you have something concerning induction reasoning. Okay? It was this one here. What is the meaning of the induction reasoning? It's something we are going to do, okay, not that much, but sometimes, okay, in this course, okay? So I want to prove a property for all n. So a priori, if you have to do this, you have to prove it for 0, n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. And you have to do all the cases, okay? In general, it may be that long to do this, okay? The induction reasoning, okay, will allow you to do the same in 2 steps, simply. First, initialize reasoning, that is to prove that my property is true for the first term here, that is n equal to 0 here in my statement. And then to prove that if it's okay for n, it will be okay for n plus 1. And in this way, the induction reasoning will tell you that it will be true for any n. So, I prove that it is true for n0. I prove that if it is true for n, it's true for n plus 1. And so I prove in this way, using the theorem, that it is true for any element n in capital. The proof of the induction reasoning is not that complicated. Huh? It's just by construction of the natural number. What are the natural numbers? 0, 1, 2, 3, and so on. So a priori, if I want to give a list of the natural number, I have to give a list of 0, all the elements, 0, 1, 2, 3, and so on. But in fact, I have another way to describe this set. I can say that I start from 0, and then I make jumps of 1. And in this way, you have everybody with only 2 operations. Okay? This is exactly the basis of the induction reasoning. If you prove that you can start and that you can pass from one to the next one, I can start to the next one, the next one, the next one, the next one. I have everybody this way. Okay? So it's typically the induction reasoning. So it's the first one, so I will write it very correctly as you have to do in an exam, for example. Okay, so I initialize the reasoning, that is to prove what happened for n equal to 0. So just a remark, because I had the question before, so for me it's an n here. Okay, so it's the way I write, I'm sorry about this. So for me, this one is this one when I write, okay? So when I do slide, no problem, okay? And this one is m. So it's a notation in the course, okay? This one is n, this one is m when I write on the board, okay? So if you are not okay with this, okay, I can give you the contact of my teacher when I was 5 years old, okay, and tell her that, okay, it's not that correct, but now it's too late for me to change, okay. But fortunately, the list of exercises are using LaTeX, okay, the exam and the midterm will be not with writing things, okay, and it's the only thing, okay, but it's a little bit strange in the way. So here it's an n, okay, the same as here. Okay. So for n equal to 0, what happens? So I have an inequality to prove, okay? So what is the first term here? I have, in fact, if I take n equal to 0, it means that in my union I have a single set. Okay? So for n equal to 0, so I repeat that I will write it very correctly because it's the first time I do an induction. After I will go faster, okay? I have this one. Because n is equal to 0, so I have a single set in my union. Simply A0. For the sum the same. In fact, if I take equal to 0, I have a single term in my sum. And of course, here, it's not that complicated to see that, in fact, I have an equality, and so that I have the inequality I want. This one is less than this one, because they are equal. Okay? So it means that for n equal to 0, I have done the job. Okay? So this is the initialization of my reasoning. I prove it for n equal to 0. I prove it for n equal to 0. Okay? Now, let's do the second part of the reasoning, okay? The second step, what we call the heredity, okay? If it's true for n, it will be true for n plus 1, okay? So heredity, and I can write it this way, pass from n to n plus 1, as I have explained with my little picture. You do jumps of 1, okay? So what will be my hypothesis here? My hypothesis is that what I want to prove is true for n, and my job is to prove that it is true for n plus 1. So my hypothesis is this one. And what I want to prove is that I have the same thing with n plus 1 instead of n. So my job will be to pass from n to n plus 1. And you see that I use the symbol of the sums in this course because it is one of the prerequisites of my course. Huh? Sums, integral, you have to be okay with them. Okay, so I have this one, I have to prove this one. Okay. So let's start with what I have here. I start with the left part of the inequality I want to prove. So the problem is that what I want to do is to use my induction hypothesis, the fact that I have the job for n, not for n plus 1. And as usual, okay, when you do an induction, you have to make a link between what happened for n plus 1 and what happened for n. Okay? In other words, that is how to make appear this one. It's not that complicated because you have a union here. This one means A0, union A1, union A2 until an plus 1. In fact, I can cut this or separate this union in two terms. I can write it as the union of the AI from 0 to n, but if I do this, I miss someone, that is an plus 1. I have this. I separate my union from 0 to n plus 1 into the union from 0 to n and the last set. That is an plus 1. So it means that I have two sets now. I have two sets. But I have some properties concerning probabilities. So if I come back to the slide of the first session, okay, in particular this consequence here, you have the point number d here. And what the point number d tell you is that the probability of the union is equal to the sum of the probabilities minus the probability of the intersection. In particular, a probability is a positive number, meaning that the probability of the intersection is positive. So the probability of the union is equal to the sum minus a positive number, implying that for two sets, the probability of the union is less than the sum of the probabilities because of the small d. And so I can apply my result to this situation. I have two sets here, this union and this one, using what I have written on the top of the board here. I can write it this way. Have in mind that for the moment I have used nothing. That is, I don't have used my induction hypothesis. It's true every time here. I have just used my proposition that is a consequence of the definition of what is a probability. How to conclude? I hope that one time I will have to use my induction hypothesis. It's now. Why? Because I know this. It's my hypothesis, my induction hypothesis. So I can apply to this term. I know that the probability of this union is less than the sum of the probabilities. So using the induction hypothesis here, hypothesis. This one is less than this one. And I don't have to forget this term. And here, I can regroup the term in a single sum because here you are from 0 to n, and it's the same as the sum from 0 to n plus 1 because for I equal to n plus 1 you have exactly this term. And you have finished the reasoning this way. So when you do this, you have proved that for any n you have the inequality you want. Because I have proved it doing an induction reasoning. Okay. So I prove it for n equal to 0, I suppose it for n, and I prove it for n plus 1, and I have my result. Okay. So don't seem to be surprised because in the prerequisite the slides you have induction, in my summary list you have inductions with the correction of the inductions. So I hope that it's not the first time you see this kind of reasoning, okay? And also not the first time that you handle this kind of thing, because you have also in my website a reminder concerning how to handle sums, okay? So I have this one. So do you have some question concerning this? In fact, what is interesting with induction is that when you have something to prove that is a property indexed by the natural number, okay, induction is not mandatory to prove something, but it may help you. If you don't know how to start a reasoning, the interest of using an induction is that you have a structure in the reasoning. I have to prove that it is true for the beginning, initialize. Then I suppose that it's true for n, and I prove it for n plus 1. So you have the kind of sketch of the proof, okay? That may be more comfortable than to try to find a direct solution without knowing how to start. Okay? So this is the interest of induction reasoning. And of course, the price to pay is that you need to have here natural number, let's say. Because the proof of why the induction reasoning works comes from the structure of the natural number. If you have a property to prove for all x belonging to R, prove something, you can't use an induction. It's true for. Okay? Okay. So no questions? No? No questions. If you don't have questions, I continue. I continue with what? I continue with the end of my little exercise, okay? That is now to extend this result in the case where n goes to plus infinity. So I repeat, do you have questions here? No?
Can we start with the sum?
Oui?
With the sum. Oh, can we start with the sum instead of the unit?
If you want. You want, yeah. You can, if you want, you can start from this one. Okay? So write this one, and this one, yes. But it's not that natural to do this. In the sense that you want to compute or to have a bound for this probability, and in fact, you can do, it's not the way I will, but you can, if it's clearer in your head this way. But I said that here you have a natural, okay, link between the two. I think that it's better to start from the last part, but for you it's better, okay? Because in general, okay, this inequality is used in this side. The probability of the union is less than the sum. And not that the sum is greater than the probability of the union, but of course it's equivalent, so. But you need to respect all the steps, okay? Right, this one, this one, this one, this one. Okay? Works this one. I may erase. Yeah? So it's what I have. and what I have proved. Now, in the second step, I want to prove that, in fact, that I can pass to the limit in this. That is, I can write okay. So in the first question, I have proved that it is true for any L, so for n equal to 0, n equal to 1, n equal to 2, and so on, okay? And I want to prove that it's true. So when I replace n by plus infinity, that is when I take the limit, okay, in the fix. Okay. So I start from what I know, and what I have previously proved, okay? I know that I have this. That is true. So I have an inequality, and you know that when the limits are well defined, you can pass to the limits in inequalities. It's just like if you have two sequences here, un and vn, un is less than vn, okay? So if there exists, the limit of un will be less than the limit of vn. So I have the right to pass to the limit here. And in fact, here the limits are well defined because it's just the limit, okay, of sums of positive terms. So I have something that is increasing, okay, whatever. So infinity here. Huh? Okay, what happened for the second part of the inequality, the limit of the sum? But what I call an infinite sum in maths is just the limit of the finite sum. It's just a notation. This element here is by definition the limit of the finite sum when n goes to plus infinity. So this one is by definition of what is an infinite sum, this one. So I have nothing to say about this term. Limit of finite sums is what we call the infinite sum. Once again, it is reminded in the little document concerning sums I have put in my website, okay? At the beginning of July. So my problem is with this one. Because I have a priori no result concerning the fact that I can do inversion between limit and probabilities. I don't know. Okay. So if you write equal to the probability of the infinite union, it's true, but you don't explain to me why. Okay. And in fact, the explanation will come from this. Is this one here. So what is the meaning of this theorem here? It means that in two very particular situations that are, I have an increasing sequence of set or a decreasing sequence of set, I can specify what is the limit of the probabilities. More precisely, if I have an increasing sequence of set, the limit of the probabilities is equal to the probability of the infinite union. And if I have a decreasing sequence of set, the probability of the intersection is equal to the limit of the probabilities. Results that are nice, but with two particular hypotheses that are to be increasing or decreasing. Okay. So if I want to use such a result, that is in some sense a kind of inversion between limit and probabilities, because when you have an increasing sequence, okay, the limit intuitively is the union of all of them, the biggest, and when you have something that is decreasing, the limit is intuitively the intersection that is the smallest I can leave from all of them. Okay, so if I want to use my result, I need to have an increasing or a decreasing sequence here. So do we have on the board something that is increasing or decreasing? Yeah? So I define Bn, so definition, I define Bn as the union from I equal to 0 AI. Okay? This set is this one. I can say two things. Of course, I have an increasing sequence because Bn is included in Bn plus 1. Each time you add a set in the union, so you are bigger and bigger. You add a set in the union. Okay, so you have an increasing sequence here. It's Bn plus 1 here. You have an increasing sequence, and what is the union of all the Bi here? Well, if I do the union of all of them, since they are built from unions of the AI, in fact, simply, the union of the Bi is just the union of the AI. When I do A0 union A1 union A3 is the same as if I do the union of A1, the union of A0 union A1, and the union of A0 1 and U2. So I have an increasing sequence of sets fulfilling the fact that the union of all of them is just the union of all the capital A. And if you see this, in fact it's finished now because I have the right to use my theorem, because I am in the statement of my theorem. I have something that is increasing, so I know that the limit when n goes to plus infinity of P of Bn is equal to what? That from the first statement it's equal to the probability of the union, that is the probability of this set. So I have exactly what I want. Because here you have the infinite sum, and the limit of this one is the limit of the Bn, and is equal to the probability of the infinite union. Okay? So in fact, you see that I use this theorem here just in order to justify the fact that I can pass to the limits. And it's the case because here you have an increasing sequence. Okay? So this one by induction, because I want to prove it for all n. One natural way to do the reasoning is to use an induction. To pass to the limit, use this kind of result, theorem 4. Okay? And I repeat that here, it's the theorem 4 I use. Okay? Why I can use it? Because I have a sequence Bn that is an increasing one. Okay? So more important is to be able to do the first step here, induction. I want you to be able to do induction. After the break, we are going to do again induction. Okay? I will correct some exercise of the summer list, okay? In particular, dealing with induction. So concerning the basic definition of a probability, it will be finished for the course here. Okay? So a probability will be for me something such that P of omega is 1. I fulfill the sigma additivity. That is, if I have a sequence of pairwise division set, the probability of the union is equal to the sum of the probability. I know that from this definition, I have these basic properties that we can use. Okay? So this theorem is more anecdotic in this course. Okay? I won't use it a lot. Okay? But I want to show you that it may help us if I want to pass to the limit. Okay? And and the definition of independence. So what I have seen, in fact, just the definition of what is the probability and some rules of computations and the definition of independence. Okay? So I will close these slides, okay? And we are going to continue just a little the course before the break, dealing with what we call conditional probability. Once again, it won't be that long, this part. For most of you, I know that it is just a reminder, but the idea is not to come back from the beginning, because I have some prerequisites in the course, okay, but to come back at the lowest level I can in order to finish my program, okay? May I erase the board if you don't have questions? So I repeat that you don't ask questions, huh? I hope that it will change. Okay? For you, for me, for mine, okay, but yeah.
Maybe it's too stupid, but
No stupid questions, only stupid answers. Okay?
okay. By definition, why we said BN?
No, I just give a name to this one.
We can say.
I give a name. So it's more than a definition. If you want, it's a notation I take. I have this set, I give it a name. I have the right to give a name
You
to.
could say anything else for BN, for example.
If you want to call it, I don't know, Mr. Choro, you can call it Mr. Choro, okay? So you give the name you want. Since I had A here, I have used B, okay? But you can use C, X, what you want, okay? It's just something that is indexed. It's a notation that I use in order to lighten a little the way I write the things here. Okay? But of course, when I use a notation, so 2 remarks. The notations that are in the course will be the one that I will use in the midterm and the final. So I want you to use them. And this one, not other one. Okay? So don't create notation from things that are in the course. When you do a reasoning, okay, if you have to give the name of someone, okay, of course, use what you want. So ask this kind of question in the beginning, okay? They are not stupid questions, in fact, okay? Yeah.
So for this reasoning,
Yeah.
the second part refers to infinity.
Yeah.
To use the theorem, the full theorem, can we always assume that there will be an increasing sequence?
No.
So that,
No, in general, when you are going to work with a sequence, it won't be increasing.
so with the proof, we will have
Ah.
to write
If you want to use the theorem, you have to deal with an increasing or a decreasing sequence for sure. So you have to find in your statement if you want to use something that is increasing or decreasing. Okay? So it's not an hypothesis, this one. It's a consequence of the Bn I define. Bn is increasing. Okay? It's not an hypothesis. So of course, more precisely, when you want to use a theorem, you have to check that the hypotheses are okay. If you change, if you are not in the statement or in the framework of the hypothesis, it won't be possible for you to use the theorem, for sure. Okay, so conditional probability. So you will see that it will be few definitions and the way to come back and to handle once again the definition of what is a probability. Question?
Just to build on the sequence question, since you were dealing with this probability going to plus infinity, like, is it not always going to be an increasing sequence if it goes to plus infinity?
No, not always, but you have a way to do it here. Okay, now. But in general, okay, when you are in the framework of probabilities, if you want to invert between a limit and a probability, yes, in general, you will be in the case of something that is an increasing sequence or a decreasing sequence. Okay? But I repeat that it won't be the main part of my course, this one. It's a result. I give you an illustration of this result, okay? Maybe 1 or 2 times I will use it, okay? It won't be the keystone of my course, okay? You have to know the definition of the probability, the properties, okay? The basic properties, and the definition of independence. It's what you are ready to know from the first part of the slide. Okay? Now too much question, in fact, so you have to find the mix. Yeah. So it's not if, huh?
Okay, it's increasing. So
It is increasing.
think AI is increasing. How can we equal to AI?
Oh, it's not what I write. No. I don't write here that BI is equal to AI. It's not what I say here. Bn is equal to A0 union A1 union An. It's not An. I just say that when I take the union of all of them, it's the same that taking the union of all of the AI. It's not the same thing here. Huh? I have never written that AI is equal to BI because it's not the case. Of course, because my BI is increasing, and for AI I have absolutely no hypothesis. Okay? Question? No? I erase. So, to deal with the conditional probability, once again, we are going to have, let's say, not a theoretical, but a definition, okay? But I want to make the link with between the definition and the intuition, what may happen in real life, okay? Because it's exactly what we can do when we speak about conditional probability. So let's take an example. That is this one. So it's not possible to replace QEM by MMEF. That's why I use QEM here. Okay, you are going to understand why. So suppose that you choose randomly a person in the world. Okay? Each one has the same probability to be chosen. Like in the case of paradise, let's say, but in the case of humanity. Okay? You choose one. And I define two sets. The set of the QM students and the set of people in Paris. Why not? Okay? So if I do a little picture, a very bad picture, here you have the world. Not a good picture of the world, but it will be mine. I have the set of the QM students. And the set of people that lives in Paris. Okay? Why I have said that it's not possible to change QM into MMEF? Because I know that all the MMEF students are in Paris, and it's not what I want to have in my example. QM are in Paris, in Venice, in Barcelona, okay? In Poland. Meaning that A is not included in B. Okay? I have this situation. A is not included in B. And you have here what we call the intersection, where you and some of you and the QM student that's here that do their second year in Paris, okay? In one of the master 2 of the program. Okay. So in general, okay, but it's possible for me to compute P of A. I have to count how many QM students, okay. To compute the probability to be a Parisian, it's possible also. I just need to have the number of Parisians I have, okay, in the city, and so on. But now, I suppose that I have a little bit more information than this one. I suppose that we know, I don't know why, but I suppose that we know that the person I have chosen is a Parisian, lives in Paris. I have an extra information, okay? And what I am interested in is the probability to be a QM student if I know this extra information, okay? So what is the meaning of having an extra information? At the beginning, I choose someone in the world. So I am in this situation, okay? With my extra information, I know that what I have chosen is necessarily someone that is in B. Okay? I have chosen a Parisian. I have this information. What is the consequence for my picture? I can erase all the people that are not Parisians. That is, I can do this. I erase this one, this one, so I keep the definition of the intersection here. In fact, I changed my universe. At the beginning of my statement, my universe was the world. I have an extra information, I reduce my universe to be Paris. Okay? So it's exactly this picture you have here. And now, I am interested in the probability to be a QM student, knowing that I have chosen a Parisian. I give a name to this probability. It's what I will call P of A given the extra information that is to be in B. Okay? And I ask you to compute this. So with words, I want you to compute to be a QM student if I know that you are a Parisian. What you are going to do concretely to compute this probability? The probability that you are a QM if you are a Parisian. But you are going to count what I have here. That is you and your friend in the second here. Okay? So I will count the number of Parisian QM students. Okay? And I will divide by what? By the number of elements in my new set of information, that is Parisians. Over this is the intuitive meaning of conditional probability. That is just extra information gives rise to a change in the universe. Okay? Extra information gives rise to a change in the universe. But I have a problem with this formula here. Because here, it's a formula that is related to counting. I count. So it means that it is a formula that is more related to the intuitive notion of probability. Count element in a set. Okay? And I don't want to be in such a restrictive situation. I want to extend a little bit more this definition. But it's not that complicated to do. If I want to remove the fact that I count elements, I multiply by n of omega and I divide by n of omega. Okay, the number of people in the world, if you want, omega was my initial universe. And this formula can be simply writing as that n of A intersected with B divided by n of omega is what I have called P of A intersected with B, divided by what? N of omega over n of B is just 1 over 0. And here you have something, a formula that is totally equivalent to the previous one, but in which doesn't appear the fact that I count element in sets. And it will be the definition of the conditional probability we are going to see. Okay? So it's important to have this in mind, and typically because we are going to extend this notion later with the notion of conditional expectation, but the idea is always the same. Compute things having an extra information. Okay? Computing things having an extra information. Is my little introductive intuition okay for everybody? So now I can pass to the definition. That is not an abstract one because it is related to what I have said here. I define the conditional probability of A given B by the probability of the intersection over P of B. And of course, if I want to do this, I need to suppose that P of B is not 0 because I want to divide by it. And P of B is here supposed to be strictly positive. Probability is a positive number. If I don't want it to be 0, I take it to be strictly positive. Okay, so this is the definition of the conditional probability. Maybe a little exercise before to see propositions and so on. Okay? So I continue with my list 3 of exercises. Okay, and we are going to take a little exercise with drawing balls in a box. Okay, it's the exercise 7. No. Exercise 7 of the list 3. Okay. just something that will be in relation with my definition of conditional probability C. You are in the following situation. You have a box, and inside you have R red balls and B black one. Okay? So suppose that you have a black box, okay, with inside red balls and black balls. Okay? So a ball is chosen at random from the box, okay? And then a second ball is chosen from the remaining balls. It means that you do this without replacements. Once a ball has been chosen, you keep it. Okay? But I want you to find the probability of these two events here. The probability that both of them are red, okay? And the probability that the first is red and the second is black. Okay? So what interests me is not the answer, is the way to write the solution of this. Because typically we are in a situation where if we want to write properly the things, we have to deal with conditional probability. Why? Because we have what happened at the first stage. I choose one ball, and I know that if I choose one ball at the beginning, it will change the composition of my box. So it will change my universe. So I am typically in the case where I will have to deal with the notion of conditional probability as explained here. Okay? So in order to lighten the way to write the solution, we are going to introduce some notations. Okay? We are going to define some sets. I will use B once again here, and I will use B for black and R for red. Okay? So I introduce some sets here. I introduce B1, that is the set where the first ball is black. B2, the second ball is black. You have understood. R1, the first ball, red. R2, the second is red. Why I introduce this? Because, okay, I am able to express what I want to compute now using my notations. In small a, what I want to compute? I want to compute the probability that both are red. Okay? And what is this using my notation? Both are red. How I can express it using my notations here. So I want to compute this. First red, second red. Intersection, end. Okay? So it's what I want to compute. In the second case, I want to compute what? First red, second black. First red, second black. Okay? So it's what I want to compute in both situations. And you see that introducing this notation, so if you want you can change the notation, but here I have just used B for black and R for red. Okay? And 1 for the trade. Okay. But I want to compute this one. Are they independent? Because if they are, it's not that complicated. The probability of the intersection is equal to the product of the probability. Okay, and I can compute the probability of each of them. So my question is, are they independent? I know. Because when you do the first drawing, you modify the composition of the box. It's not possible for them to be independent. And it's possible to prove that they are not independent. Okay, but intuitively I don't have independence because, okay, when I first choose a ball, it modifies the composition of the box for the second drawing. Okay? So I want to compute this. If I have a look on my formula on the right part of the left part of the board, I have the intersection here. And in fact, using the definition of the conditional probability, I can express the probability of the intersection using the conditional probability. P of R1 intersected with R2 may be written from the definition of the conditional probability as the probability of R2 given R1 times the probability of R1. I use this formula with A equal to R2 and B equal to R1. Okay? Okay? By definition of the conditional probability. And now what we are going to be interested in is that it will be easy to compute each of the term here. Each of them. Okay? So are you okay with what I have written here? It's just a consequence of my definition of what is conditional probability. I just multiply by B here and I obtain PB times this one is equal to P of the intersection. So I repeat, are you okay with what I have written here?
Is the order okay?
Hmm?
Is the order okay? Because the
Is zero?
Or the order. It says probability of R1.
I don't mean the order. In which? In this one?
The first one is P of R1 intersection.
No. Here, this one, so I answer in two steps. When you do an intersection, okay, the order doesn't matter. Okay? A union B or A intersected with B is the same than A intersected with B and A. So you can change the order in the union. Okay? Because keep in mind what is the definition. The union is the set of the elements that belong to at least one. You can change the order. For the intersection belongs to both. You can change the order and change nothing.
What about from the other side?
For the other side, okay, I am agree with you that in fact it's possible to write several formulas. This one is okay, but if I remark this, I can also write, for example, this one, P of R1 given R2 times P of R2. Both are true, but one is more clever than the other. Because what I do, when I draw balls, first I choose the first one and then the second one. So it means that this term to compute here, the probability that the first is red, knowing that the second one is red, is something that is not that natural to compute. It's possible to compute, but not that natural. Because here, easier because I will have an information with respect to my first drawing, and now I will be able to compute the things. Okay, so this is true, like this, but in some sense, meaningless in this situation. Because 1 and 2 here represent the first and the second drawing, okay, it will be easier and easier to compute this one, a priori, than this one. Okay? So that's why I write this one here. Because second stage, first stage. Okay? Here, P of R1 is equal to what? What is P of R1 here? But I choose one ball in the box. How many balls in the box? A plus B. A red, B black. So at the beginning, I have in my box R plus B balls. And I want to compute the probability that I choose the red one. How many red? R. R1, okay. R1 means the event I choose the first ball that is red, okay. So what is the probability that my first ball is red? So P of R1 is equal to the number of red balls at the beginning over the total number of balls at the beginning. This one. R over R plus B. Okay? I repeat, because at the beginning I have R red, B black. Okay? Second term to compute. I know that I have chosen first a red one. So what is the new box? In the new box I have B black and R minus 1 red, because I have chosen one red. So I remove it from the box. So when I have this instrument information, it means that I have first chosen a red one. Okay? So when I will do the second drawing, I will have in my box B black and R minus 1 red. So what is this probability? I have a new box with inside B black and R minus 1 red. To compute the probability that I choose a red one, how many red? R minus 1 over the total number of balls in this situation, that is B black plus R minus 1 red. That is B plus R minus 1. And the probability I want to compute is just the product of this term and this term. Okay? The product of this term and this term. So it's not the only way to do, but I think that it's the better way in order to explain it, okay, clearly, using the notion of conditional probability. Question?
I have found the answer. Thank you.
Okay? So, I can write here that I obtain R over R plus B times R minus 1 over B plus R minus 1. And for the second, I will do it directly, and after we are going to do the break.
Sorry, one question.
Yeah.
Can we also think about it in the same manner yesterday we thought about cards?
I prefer not to.
Okay.
I prefer. The problem is that, so I repeat what I have said before, is that in this way it's very clear. In the sense that I see what happened. If I choose a red one, I have a new composition of the box, and so on. Of course, it's not the only possibility. You can, okay, do a direct reasoning, saying that you choose two balls, okay, among this one, with order, okay, and without repetitions, and try to say something. And it's possible, of course, to obtain the same thing here, using the kind of reasoning I have done in the case of cards when I take two cards. Yes, but be careful. It's just my advice. Okay? Because in this situation that is that simple, okay. And because also here, okay, you have just one formula to write, and after it's very, very simple. Don't have to explain that I do something, okay? But yes, you can. And for this one, and after I do the break, so it's exactly the same thing. So if I use the same formula, then this one, okay, for this situation, it's P of B2 given R1 times P of R1. So what is the probability of R1? Well, I have already computed, so I have to choose R among R plus B. It means that I have first chosen a red one. Second step, I have chosen a red one, I want to choose a black. What I have in my new box, B black, R minus 1 red. What is the probability to choose a black in this situation? It is just B over R plus B minus 1. Okay? And with this little exercise, okay, I hope to make you understand that intuitively, computing a conditional probability is changing my universe. I modify my box, so I modify my universe for the second drawing. Yeah.
For the end of the part B, wouldn't it be B plus R minus 1 because you already took the right one?
Yeah, it's it's the same, huh? It's B plus R minus 1, yeah. I have it written here, R plus B minus 1.
Oh, okay.
But you're right, huh? It's the number of black, B, plus the number of red, R minus 1. Okay? It's the same. Okay. So break. 10 minutes we do. So let's come back to the course. For the moment we have seen the definition. Okay? And now we are going to see some propositions related to this definition. Proposition 6. So I suppose P of B to be strictly positive in order to be able to define the conditional expectation, conditional probability of A given B. And I say the following. So it's proposition 6. A and B are independent. I use the previously introduced notations. A and B are independent if and only if P of A given B is equal to P of A. So this result is that intuitive. If you think about a conditional probability as something you compute having an extra information, okay? I have the extra information B, and I compute the new probability. But if the two events are independent, okay, having this extra information or not changes nothing, okay? So to give you an example, okay, the probability that you will have a good mark at the final exam, okay, given the weather will be sunny this day, is just the probability that you will have a good mark at the exam, because sunny, rainy, okay, has no impact a priori, okay, on the way you are going to do the exam. So why I have this? Well, it's, in fact, I have nothing to say except come back to the definition of independence. What is to be independent? By definition, to be independent means that the probability of the intersection is equal to the product of the probabilities. Okay? It's the definition of independence. So I have this. By definition, P of A given B is equal to what? By the definition in red in the slides here, P of A intersecting with B over P of B. And so, in fact, it's finished. Why? Because if I am independent, the probability of the intersection is equal to the product of the probability, and I can do simplification between P of B and P of B, okay? And in the converse, if this one is equal to P of A, the probability of the intersection is equal to the product of the probability. So in other words, P of A given B equal to P of A is equivalent to the fact that P of A intersected with B is equal to P of A and P of B. So independence and the fact that the conditional probability is none other than the probability itself are equivalent. Okay? So to prove the independence, you can come back to the definition, or from now on, compute the conditional probability and prove that it is equal to the probability of the set. Okay? Something that is purely equivalent. Okay? So just come back to the definition to prove this. Are you okay? Just write the definition of independence and see that this one equal to P of A is equivalent to this one, that is the definition of the independence. Okay? So if you are okay with this point, second point, okay, everybody? So second point, it will be the way to remind, okay, and to handle a little the definition of probability. So in the second statement, we say the following. I define a new mapping that I call PB, P to the power B. Okay, that is a mapping from A into 0, 1 that is defined this way. To any set A, I associate P of A given B. Okay? I associate to each set, okay, the conditional probability of A given B. And I said that, this is the aim of my statement, PB is a probability. PB is a probability, okay? So in fact, keep in mind that initially I had a probability that was P, and now I defined a new one called PB, and the name of this one will be the conditional probability given B, okay? And what we are going to prove here is that we have already in the probability in the sense of the definition I have introduced the previous session. Okay? So if I come back to what I have introduced in the previous session, I have no more the slide here. Let's do the, okay. I come back to my website. It's here. QM. Okay. So you have everything here. Okay, and I remind that here you see that you have the video of the first course, and you will have the video of the second one, okay, at the beginning of the afternoon, I think. Okay. And I come back to the slide number 3. Okay. That are this one. Back. Okay. Just to have the definition of what is a probability. So to prove that PB is a probability, I have to prove that the definition 7 is fulfilled. Okay, so I have 2 points fulfilled, that PB of omega is equal to 1, and that if I have a sequence of pairwise Dijon set, PB of the union is equal to the sum of the PBs. The only underlying hypothesis I have is the fact that P is itself a probability. Okay? So I have 2 points to prove. What is PB of omega? I use the definition of PB, this one. So it is P of omega given B, by definition of the conditional probability. It's P of omega intersected with B over P of B. But what is omega intersected with B, knowing that omega is the universe, that is the biggest set? What is omega intersected with B? B itself, okay? So I have PB over PB. I have 1. So I have checked the first point in my definition. PB of the universe is equal to 1, of course. So this is the first point in the definition of probability. Do you have questions? Questions, please. Questions?
In the past, I have some misunderstanding of the increasing strength, but now I understand.
Okay. So be careful, because if you want a video that is fluid, okay, ask me the question. Okay, you have something that is better. So for you it's okay because you know what was the course, so when you will see the video. But imagine some student, okay, I don't know, somewhere. Okay, do you have a question? Some strange. Okay, so ask me the questions, the better you can, and I will answer. Okay? So second point, I have to prove what I have called the sigma additivity. If I have a sequence of pairwise disjunct sets, then the probability of the union is equal to the sum of the probability. So let's start with a sequence of pairwise disjunct set and see what happens. So let AN be a sequence of pairwise disjoint sets. Okay? And I am interested in PB of the union. So I use the same notation here. I am interested in this one. Okay? What can I do to start with? Okay, but I can just use the definition of PB. Okay, so by definition of PB, this is equal to the conditional probability of my union given B, and I have the definition of what is the conditional probability. What is the conditional probability? It is the probability of the intersection over the probability of B. I write it this way. I have this. Okay? I have this one. If you remind the little exercise we have done together 2 days ago, that was the exercise 5 or 7, I don't remind. This one, the exercise 5, okay? We have seen some rules of computation of this situation here. If you take the second line, you see that to do the intersection between B and the union is the same than to do the union of the intersection of the B and the AI. So using the exercise 5 of the summer list, the first probability, I use this, okay, here. This one, too much material. This one here, okay? I use this one. So I use this one here. It's the probability of the union from I equal to 0 to plus infinity of AI intersected with B over K. Okay? For the moment, there is something that I don't have used, and that is important. I don't have used the fact that P itself is a probability. I don't have used the fact that P itself is a probability. That is something that fulfills what is written on the slide here. But if I want to use a formula concerning P of the union, I have to come back to the definition, and I have a nice formula if they are pairwise disjoint. Is it the case? So I am interested in these sets here. If I want to use a formula of the type the probability of the union is equal to the sum of the probabilities, I have just to check that they are pairwise disjoint. My question is, are they pairwise disjoint? And if yes, why? You have something in the border. I start with a sequence that is not an arbitrary sequence. Here, I have a sequence of pairwise disjunct sets. If you have pairwise disjunct set, meaning that they are with an intersection empty 2 by 2, okay, it's the last line of the slide here. But what happens if I do the intersection with a fixed set? I will have exactly the same property. If A1 intersected with A2 is empty, A1 intersected with B, intersected with A2, intersected with B will also be empty. Okay? So from the fact that this sequence is pairwise disjoint, meaning that the sets are disjoint 2 by 2, here I have also pairwise disjoint sets. Okay? And since I have pairwise disjoint set, I can use the fact that my P is a probability. And so that I can use the second point in the definition. The probability of the union is equal to the sum of the probabilities. Okay?
Could you explain it?
Hmm?
Could you explain it?
Again, what?
The fact that I understand that AI, they are overlying.
So, you understand because it is my hypothesis.
Yeah.
I suppose it to be pairwise disjoint. And what I say is that if they are pairwise disjoint, I have something here that is a sequence of pairwise disjoint set. And why? Well, let's denote by Ci these sets here. AI intersected with B. It's the sequence I am interested in here. Okay, I just give a notation for them. If I want to prove them to be pairwise disjoint, I have to be interested in Ci intersected with Cj for I different from J and see what happens. Just replace by the definition. It's AI intersected with B. AI intersected with B intersected with AJ intersected with B. But I said that the AI is a sequence of pairwise disjoint set, and by definition, last slide of the slides, pairwise disjoint means this one. So when I do this intersection, I have the intersection of AI and AJ, because you know that when you have several intersections, you can do the intersection in the order you want. Okay? And so this is empty.
I understand that the intersection is pairwise, but
Is
pairwise disjoint, but
which one?
the intersection of
No, intersection pairwise disjoint mean nothing.
yeah, I mean the I with B, but B with I there's intersections.
No, I repeat. Here I have an hypothesis. My AN are pairwise disjoint. The meaning is here. This is the meaning of being pairwise disjoint. I take them 2 by 2 and I obtain an intersection that is empty. Okay? It's the definition of being pairwise disjoint.
If
So,
you do it with B, it's not
No.
empty.
I don't have this with B. Okay? I just said that. I start from this one, step by step. Let's do it. I do a little computation because I want to prove this for what I have defined, that is PB here. So I do the job. And I see that when I do my computation, I have this stage here. What I want to do is to use this property, that is true for any sequence, but if my sequence is a sequence of pairwise disjoint set. So if I want to apply the formula that the probability of the union is equal to the sum of the probabilities, I have to check if these ones here are pairwise disjoint. It's exactly what I said here. They are pairwise disjoint, so I can use this formula, and it's what we are going to do. If you take the intersection of two of them, that is exactly what I do here, I obtain empty set. Because the intersection of the first and the third is empty. So when you do intersection of other things, okay, it will be for sure the empty set. Okay? It's basic rules of computation of intersection that are reminded in the slides of the prerequisites. Okay? Is that clear?
Yeah, but it's just HJ with intersection with B, it's not empty.
The intersection about what and what?
HJ and B.
Of course not. It's not what I have to check. No, of course it's not. But it's not I expect to have. Okay?
Yeah, that was my question. They are not pairwise 2 by 2, but they are.
You see, 2 by 2. If I consider this family of sets, 2 by 2 doesn't mean A, I, and B. Of course, they are not disjoint. But if I consider this family of sets, they are disjoint 2 by 2. Okay, 2 by 2 means among this family here, not between all the sets in my statement. Okay? So AI and B are not disjoint for sure. Okay, but these sets here, the intersection between AI and B define a new family of set I denote by this one, Ci, and here I have a sequence of pairwise disjoint set. It's what that interested me, because what I want to use, that since I have a sequence of pairwise disjoint set here, the probability of the union is equal to the sum of the probabilities. Okay? So, it was just my little remark to say why they are pairwise disjoint. And now, I continue my computation here. I use the fact that the probability of the union is equal to the sum of the probabilities because they are pairwise disjoint. So I write the sum from I equal to 0 to plus infinity of the probability of AI intersected with B over P of B. And now to conclude, what I have to do, I just come back to the definition of PB. What is PB? It's just the conditional probability of A given B. So here I have PB of AI. At the end, what I have proved that if I have a sequence of pairwise disjoint set, the PB of the union is equal to the sum of the PBs. I have proved that the second statement in the definition of a probability is fulfilled. So I have proved that PB is a probability. I have an initial one that was P, I have a new one. This new one is called conditional probability given B. Okay? So I repeat that it's very important to take time at the very beginning, and in fact, okay, that's why I have sent it and remind the prerequisites very soon. Because I think that at the beginning, if you had some problem, you will have some problem with the prerequisite, in fact, not with the things that I introduced. That are the way to write mathematics, okay, and the way to use basic rules of computation in sets, okay, sum or integrals, okay. Don't focus on this because I won't have the time during the course to come back every time to what I have called prerequisites. Okay? Are you okay with my proof? So I proved that PB is a probability because I have proved that it fulfills the 2 points in the definition of a probability. PB of omega is 1, and if I have a sequence of pairwise disjoint set, PB of the union is equal to the sum of the PBs. I have a probability called the conditional probability. May I continue?
I'm sorry, I didn't understand the last step, how we...
Which step?
Yeah.
This one, this one, this
Yeah.
one?
No, from... Yeah.
By definition?
Because they're independent.
No. By definition. What is PB? PB of A is P of A given B. Here, I have P of AI given B, so it is PB of AI.
Oh.
Just by definition. And nothing, I have never used the word independence here. Never. Okay? Other questions? Okay? So PB is what we call the conditional probability given B. Okay, so I have done the proof of my proposition 6. Okay? So I finished the part concerning conditional probability. That is also a very short part here by things that you know in general. Okay, you have, for most of you, already seen. That is what we call the law of total probabilities and the Bayes formula. Okay? So if you don't have questions, I erase my board. Questions?
So do you have to write the steps that you do in the exercise 5, or We write it directly.
No. Of course, here, so by summer exercise, I mean, okay, something to train. Something that is supposed to be okay for you before to start the course. So of course, you can use and you will use all the results you have in the list of summer exercises as a prerequisite. Okay? So of course, you don't have to do the proof of this one in order to use it. You use it directly. Okay? And now, okay, I can do the same remark concerning the course. Once we have seen something together in class, you can use it. If I want you to prove, I will ask you explicitly to prove. If I don't ask, use it. Okay? So the law of total probability. So in the statement of the law of total probability, you have the notion of partition. It will be the way to remind what is a partition, something that is, once again, in the slides concerning the prerequisites, but I will remind. So the law of total probability. So intuitively, I will comment just after, the law of total probability is something that will allow you to compute the probability of a set that is, let's say, that complex, okay, a little bit complicated to do directly, cutting the problem into smaller problems. This is the idea. Where the probability of the smaller problems will be easier to compute. This is the meaning of this, okay? And I will enter the details. I have a countable partition. So first, countable just means that I have a sequence. Something that is countable is something, okay, that have elements that may be represented as the element of a sequence being something indexed by the natural numbers, okay? So what is a partition? What is a partition?
Collection of sets.
Start, okay. And then?
Intersection is empty.
Oh,
And the
oh.
union is omega.
So intersection 2 by 2 is empty, otherwise intersection is empty, and?
And the union of all of them is omega.
Okay. You just miss a little thing that all of them have to be non-empty. Okay. But I am agree with you. So, in the theorem 5, okay, I consider Bn to be a partition. If I do a picture, a partition is this kind of thing. You have the universe, and you cut it in smaller parts without overlap. Okay? So you have B0, B1, B2. But here it's a finite partition with 1, 2, 3, and 4. Here you have a finite partition with 5 elements, and you see that 2 main characteristics, or 3, they are not empty. Each one is not empty. I have no overlap, meaning that 2 by 2 the intersection is empty set. And then, if I am an element in omega, for sure I belong to at least one of the element of my partition. Okay, if you take an element here, it will be in B4. Here in B0. You don't have elements that are not in one of them. This is a partition. Cut my universe into smaller parts. Okay? So if I write it correctly here, what is this? A partition. So 3 things. I work with non-empty sets. I want them to be pairwise disjoint. And the union of all of them is equal to my universe, omega. Okay? So this is the definition of a partition. Here I write what is a countable partition when I have a sequence of sets. Here, it's a picture concerning a partition with a finite number of elements. But you can consider an infinity of this, okay? And it allows you, if you want, to separate my big universe into smaller parts. And it's something that we often use when we count, because sometimes, okay, if you have to count all the elements of omega, it can be boring, but sometimes it is better to count all the elements of B0, to count all the elements of B1, and so on, and to do the sum at the end to obtain, okay, all the elements of omega. This is the intuitive meaning below partitions. So this is the definition of a partition I have reminded, I repeat, in the slides concerning the prerequisites. Okay? And I say the following. So I suppose that P of Bn is strictly positive. And why? Because we are just going, if you see the formula in red in theorem 5, if you see the formula in red in theorem 5, you have here conditional probabilities in the formula. If I want to define them, I need that these probabilities are strictly positive from the definition. So I want to prove the formula in red here. And in fact, what will be the idea? The idea is exactly this one does. Imagine that you have a set A here. That is what I have drawn here. I said that it is possible to have a formula that expresses A in terms of intersection with the element of my partition. So here, typically, I have this one. A is equal to A intersection with B0, union A intersection with B1, and so on. And why I have this? Because I have no overlap. That's why I have disjoint union. And because I miss nobody, because I know that the union of all the elements of my partition is the universe itself. Okay? It's exactly this idea that we are going to use. I have what? So I do the proof of theorem 5. I said the following. I start from A, the set that interests me. I can say the following. A is equal to A intersected with omega, because A is included in omega. Omega is the universe. Okay, so I have written nothing here. But what I know that omega is the union of all the B. So I can write it this way. A intersected with the union of all the BI, because the union of all the BI is equal to omega, by definition of a partition. Once again, we are going to use the result of the exercise 5 of the list 3, that I can use without proving it. Okay? And I have this way, the union from I equal to 0 to plus infinity of A intersected with BI. Okay, so I have written A as a countable union, and since the BI are pairwise disjoint, doing exactly the same reasoning than the one I have done just before in the preceding proof, defining CI, okay, you have exactly the same thing here. Here, you have pairwise disjoint sets. You have here pairwise disjoint sets. And so what you can use the definition of a probability. You have here a sequence of pairwise disjoint sets. You know that the probability of the union is equal to the sum of the probabilities. I use the sigma additivity property. So since P is a probability, and since I have here a sequence of pairwise disjoint sets, P of A is equal to the sum from I equal to 0 to plus infinity of the probability of A intersected with BI. I have this one. Okay? But in fact, it's finished now, if you have this. Why it's finished? But just using the definition of the conditional probability in the formula in red here in theorem 5. What is P of A given B? It's the probability of the intersection over P of Bi. And so here I have exactly the fact that the probability of the intersection is just P of A given Bi times P of Bi. It's what we call the law of total probability. What you have to keep in mind from an intuitive way is that, okay, we are in this situation. We have a set, we have a decomposition of the universe using a partition. And this formula means that if you want to compute the probability of A, it is sufficient for you to know the probability of each element in the partition and to compute these conditional probabilities. And in general, this computation, the computation of this term, will be easier than the direct computation of this one. Okay, so easy to do, easy to do. I do assume I obtain what I want. Okay? So here I have stated the result in the case where I have a countable partition, but as written in the remark here, if you have just a partition with a finite number of sets, instead of having an infinite sum here, you will have a finite sum. Okay, so if you have, let's say, capital N sets here, you will have a sum from I equal to 0 to capital N. Okay, if you are, for example, in this situation. In this situation, you will have a sum from I equal to 0 to 4. Okay, because I am in the finite case. So it's what we call the law of total probability. And the way to use in general is to say, okay, I am able to compute this one, I will compute this one. Okay? And we are going to see an example. And we are going to do exercise concerning this, okay, next week in the list 3 of exercises. So are you okay with my reasoning? In fact, so it's not that long, no? I just use here the definition of P, that is a probability, so I can use what I have called the sigma additivity. Probability of the union is the sum of the probabilities. Why I have the right to do this? Because I have here a sequence of pairwise division sets. Okay. Questions? So if you don't, let me give you an example of this. Okay? That is a typical example where, okay, you have to use this kind of formula. But of course, if you want to use the law of total probability, you need to have a partition somewhere, for sure. Or you can't. Okay? So I can say the following. So suppose that you have an item, whatever, okay? An item is produced by 3 different factories. I call them F1, F2, F3. Okay? Factory 1, factory 2, factory 3. The statement tells you the following. F1 produces 20% of the items, with, let's say, 5% of defective ones. Okay, so you produce 20% of the total production of the item, and you know that the factory 1, okay, produce the item with 5% of them that are defective. Okay, you have some default on this item. And I do the same for F2. I say produces, let's say, 50% with, let's say, 2% of them that are defective. Okay. And for F3, I don't have the choice for this one because I have only 3 factories that produce the item. So I have here 30%, and here let's say 1%. Okay? My question is, compute the probability that an item is defective. And I denote this event by D for default. Okay? So you are in this situation, and I want you to compute the probability of a randomly selected item is defective, knowing that it is produced by 3 different factories, each of them having this characteristic. Okay? What I have to do, ID? Well, of course, it is related with what I have done previously. Huh? So here I am not in the case where I have a countable partition, but I have a finite partition. Which one? What is my underlying partition of the universe here? Just have a look on the statement. Yeah. But I know that for an item I can be produced by F1 or F2 or F3. Of course, it's not possible to be produced by both of them. It's meaningless. And I know that by the percentage here, all the production is done by the 3 factories. I don't have an extra factory. Okay, I have only these 3 and no more. So F1, F2, F3, that are 3 events, B produced by F1, B produced by F2, B produced by F3, is in fact a partition of the universe. I can use the law of total probability. F1, F2, F3, if I consider these 3 events as to be built by F1, to be built by F2, to be produced by F3, F1, F2, F3 is a partition of the universe. Okay, intersection empty because it's not possible to be produced by 2 at the same time. And the union is everybody because 20 plus 50 plus 30 is equal to 100. Okay? So if I want to compute P of D, what I have to do, I use the law of total probabilities, because I have a partition of the universe. And if I want to compute the probability to be defective, what I have to do, I use my formula in red in theorem 5, P of D given F1 times P of F1 plus P of D given F2 P of F2 plus P of D given F3 P of F3. You have everything you want in the statement. The conditional probabilities here are given by the last 3 terms. The probability to be produced by F1 is 20, the probability to be produced by F2 50, and the probability to be produced by F3 30. So it is the typical use in concrete cases of the law of total probability. Okay? So you have a basic example here. We will see other ones, okay, in the list 3 of exercises, but in each exercise of this type, at the very beginning, you have to look for a partition if you want to use the law of total probability. And in general, the partition will be obvious from the statement. Here it's to be produced by one of the 3 possible factories. Okay? So you have the law of total probability with a little example. Yeah?
In the exam, do you want numbers or just...
I don't mind about numbers. Okay? You won't have calculator, you won't have no phone, you will have no computer, so Okay? You won't compute with numbers. Okay? So for me, if you write the thing this way, you will have all the points. I don't mind what is the result. But I want the justification, in particular, the fact that you have a partition. That's why you have the right to use the law of total probability. So I have this. Questions? Okay? So let's see the last result for today. That is the Bayes formula. Once again, it seems to be very big, but not that. So if you are okay with what I have written on the blackboard, okay, we are going to erase it. I can? Let's go. Okay, Bayes formula. So first of all, the framework of this theorem is the same then as the previous one. Okay, so it means that Bn is a countable partition. Okay, and I want to prove the formula in red here. And what is the meaning of this formula? In some sense, you reverse the conditionality. So it comes back to the question with R1 and R2 when you say, okay, I have the right to write the formula in two ways. P of R2 given R1 of P of R1 given R2. It's more natural in my exercise to first compute what happened in the first stage and then what happened in the second stage. But sometimes you may want to compute the other things. And you use it using this kind of formula. So what I compute here, I want to compute the probability that Bn, the probability of Bn given A. Okay? And I said that it is possible that if I know, in particular, the probability, the conditional probability of A given all the Bi. If I know these probabilities, that was 5%, 2%, 1% in my statement here, I am able to deduce from these numbers, okay, the probability, okay, of this type. Typically here, if I ask you to compute the probability that I have been produced by factory 1 given that I am defective, it's something that you can compute using this formula. So what is this formula? It seems to be very big, but in fact it's not. What is the denominator here? And I have proved previously that it's just PA. Okay? So I want to prove this one. So proof of theorem 6. I want to prove this one. First I remark that by theorem 5, I know that P of A by the law of total probability is equal to this one. It's the law of total probability. So let's start with this second member here in my equality and prove that it is just equal to this one. Okay? So if I write the right part of the equality I want to prove, I have this one, P of A given Bn multiplied by P of Bn divided by the sum from I equal to plus infinity P of A given Bi, P of Bi. From my previous remark, I know that the denominator is equal to P of A. So I have a big denominator that is in fact only P of A from theorem 5. And now how to conclude? by simply applying the definition of conditional probability. What is P of A given B? It is the probability of the intersection over the probability of Bn. So by definition of the conditional probability, I have P of A intersected with Bn multiplied by P of Bn divided by P of Bn times P of A. Here, I just use here the definition of this one. I can do simplifications between the P of Bn and what I have here. The probability of the intersection divided by P of A by definition of the conditional probability. It is just P of Bn given A. So it seems to be very complicated, but in fact I use just both the definition of what is the conditional probability of a set given another one. Okay? And it closes the part concerning conditional probability. That was a short part, okay? I just want you to have in mind the definition of conditional probability, the Bayes formula, and the law of total probabilities that we will use sometimes in this course. Okay?
For the exam and return, is there any similarity?
No. No formulary. Well, it's a choice, huh? It should be possible. But the problem is that if I give you a formulary, I will give you no point for the formula. Okay? And I prefer to give points to the student that know formulas. Okay? And in general, it's what we do in these programs. Okay? No documents would be allowed. Questions? Okay? So today what we have seen, okay, a definition of conditional probability, more or less, the law of total probability and Bayes formula. Not that much, in fact. Okay, so let's finish with the beginning of one exercise I will finish to correct next session. So I come back to the summer list of exercises, and I want to deal with the exercise 24, if I remind, and the exercise 25. This one. Okay? So this formula, so the way to develop A plus B to the power n, okay, is something that is known as the Newton formula. Something that you have probably already seen, and in particular, if you take n equal to 2, you just have the formula that a plus b squared is equal to a squared plus b squared plus 2 times a times b. Okay? It's just a generalization of this formula in the case of a power n. That's what we are going to prove, and we are going to deduce from this formula. So first question, what is this notation here? This notation is coming from the slide concerning the prerequisites. Okay? It's the combinations. So may I erase my board? So exercise 24 of the summer list. First of all, I remind you what is the definition of C and K. Okay? C and K is defined, okay, for K belonging to 0 n. C and K is what? It is n factorial over K factorial times n minus K factorial. So it's something that is explained, okay, in the second part of the slide of the prerequisites. So what is this number and why it is a special number with a particular name, C and K? Because from a concrete aspect, okay, we have a sense to this number. This number represents the number of possibilities you have to choose k elements among n without order and without repetitions. It's what we call combination. Okay? The number of possibility to choose k among n without order and without repetitions. Okay? So imagine that you have a box with n different balls inside. You choose k without order and without repetition. And keep in mind that what is the meaning of without order and without repetition? It means all at the same time, for example. Okay? Without order and without repetition. The number of possibility to do this is this one. Okay? N factorial over k factorial divided by n minus k factorial. So if I come back to my prerequisite, okay, you have everything inside here. Okay, I'll show you. It's here. Okay, the second one in red. Okay, with the explanation. Okay, and something about this. So let's come back to my exercise. So I have my definition. Okay, and I am able to do everything. So first question of the exercise, to prove that, so I take k from 1 to n, and I want to prove that, it's my job, Cn plus 1 k is equal to Cn k minus 1 plus Cn k. Okay, why not? It's an algebraic relation that you have to prove, okay? We have the definition of each of them. We are going to do the sum and see that I will cover what I want. So you have two possibilities. You can start from this one or you can start from this one, but in general, it's not always true, but in general in mathematics, we prefer to start with the complicated expression and try to simplify it instead of doing the converse, in general. And in this course, it will be most of the time the way we will do. I have a complex expression and I will try to simplify it instead of starting with something that seems to be simpler and to make it more complex. It's equivalent for sure, okay, but better in general. Let's do, okay? What is this? I do the proof here. I compute Cn k minus 1 plus Cn k. And to do this, I use 2 times the definition. What is Cn k minus 1? It is n factorial over, so I have to replace in the formula k by k minus 1, okay? So it is k minus 1 factorial multiplied by n minus k plus 1. Because I have here minus k minus 1. So it is minus k plus 1. And I have to do the sum with Cnk, that is exactly this formula, that is n factorial, over k factorial, n minus k factorial. Okay? So here I just use the definition twice. Just plugging for the first expression, okay, k, I replace k by k minus 1 in the first expression, okay, in order to have the first term. So I want to handle this term, okay? In general, when I have a sum with 2 ratio, okay, I try to put them, I try to factorize, in fact, okay? We are going to factorize what we can factorize. What you need to have in mind here, if you want to do a good factorization, is that k factorial, I remind you that k factorial is k times k minus 1 times k minus 2 and so on until n. So I can write k factorial as k times k minus 1 factorial. You have a right. Huh? K is the product of the K first integers, so I can decompose it in this way. The same hold for n minus k plus 1 factorial, that can be written as n minus k plus 1 times n minus k factorial. If I do this, I can put things into factors. In fact, I can put into factor n factorial over k minus 1 factorial times n minus k factorial. And what are the remaining terms? So if I want to obtain the first term here, the only term is missing in 1 over n minus k plus 1. 1 over n minus k plus 1. And here, I have my n factorial, I have my n minus k factorial. And if I want to have below 1 over k factorial, okay, it means plus 1 over k. In fact, I have used these two relations, okay, to put the things into factors. Okay. What can I do now? I have two ratios that are not that complicated. I can try to see what happens if I do the sum. To do the sum, I have to put them into the same denominator. That's what we are going to do. And I obtain k plus n minus k plus 1 over n minus k plus 1 times k. Okay. I have two ratios, I put them into the same denominator in order to do the sum. I have a little simplification here, because I have k plus n minus k plus 1, so I have simplification between the k's here to obtain n plus 1 over n minus k plus 1. Okay? Now I just use the definition and I try to do computations. Not that complicated. I do the job. Now we are going to see if it's possible to integrate this term, okay, into these factorial notations here. It's what I am able to do, because look at me, if I have n factorial multiplied by n plus 1, it is n plus 1 factorial. If I have k minus 1 factorial multiplied by k, I obtain k factorial. And finally, if I have n minus k factorial multiplied by n minus k plus 1, I have n minus k plus 1 factorial. And why it's finished? Because according to my definition here, you have exactly this one, that is c n plus 1 k. So I use the definition, compute a little, and I obtain what I want. So nothing complicated after. Have you tried to do this during the holidays? Everybody? Okay, so I have proved my first question. And this little question will be used in the second step, in fact, in order to compute a plus b to the power n. Is it okay for you? So it's just computations and using several times the definitions, okay? So nothing to do with probability theory, just do with computations, okay? So I have proved the first question. Do you have some question? It's okay? So if it's okay, I continue. The second question that I won't have the time to finish today, but I will start by this next session, okay? is to prove that for all n belongings to n, I want you to prove that a plus b to the power n is equal to the sum from k equal to 0 to n of the c and k, the c and k being this one, okay, time what? A to the power k, b to the power n minus k. That's what I want you to do. So I have several possibilities to do. Okay, it's possible to do it directly, coming back to the intuitive definition of this one, that is to choose k among n without order and without repetition, but it's not the way we are going to prove it today. I have something to prove for all n. Two possibilities. I have an idea, I try to do it directly. In general, for a student, it never happens. Okay? In general. Sometimes you have already seen this result, you remind the little idea, the little trick, okay, you use it, okay, but in generality, during an exam with the stress and so on, it's not the idea that you will have. I prefer to have, okay, some framework that are easier to apply systematically. And here, typically, I have something to prove for all n. What I can do? Induction. Okay? And I think that in general is the way you have to think about a property to prove for all n. If I have no idea how to do it directly, let's try an induction. Because I repeat, what is interesting with an induction is that you will have a framework in order to think. Okay? You won't be alone with your white paper and your pen. You have a way to do. Okay? So let's do by induction. So for the induction, I have two steps. Initialization, heredity. So let's start with the initialization. The initialization is to prove that it's true for the first. What is the first here? The first is n equal to 0. No, so it's n belongs to n star, so it's n equal to 1 here. Okay? So for n equal to 1, I initialize my reasoning. Okay? And I have to prove that the formula is correct for n equal to 1. Why not? So I have two terms in my equality. I have a plus b to the power 1. That is just a plus b. And I have a sum. That is a sum from k equal to 0 to 1 of what? C1 k, a to the power k, b to the power 1 minus k. I have a sum, in fact, with two terms. What are these two terms? C1, 0, a to the power 0, b to the power 1, plus C1, 1, a to the power 1, b to the power 0. What is C0, 1? I take the definition, I can plug this in, I find 1. Because 0 factorial is equal to 1. Okay? So C0, 1 is equal to 1. And if I compute C1, 1, I also obtain 1. To choose 1 among 1 or to choose 0 among 1, I have only one possibility to do. Okay? I choose nothing or I choose the unique element. So these two values are 1 and 1. So I have what? 1 times a to the power 0, that is equal to 1, plus b to the power 1, so I have b, plus C1, 1, 1, a to the power 1, a, b to the power 0, 1, b plus a. And you see that you have the equality between these two expressions. Okay? So it means that I don't have proved what I want to prove, but I have done the first step of my reasoning. I have proved that my reasoning is okay for n equal to 1. It's the beginning of the induction. Okay. It's not enough, huh? So this one is equal to this one. But it's the first step. And at least in an exam, okay, if you have something to prove, if you start an induction, then you will have a little something instead of nothing if you do nothing. Okay?
Why did we start with 0 with 1 and not 2?
Why?
Why did we start the induction with 1?
Excuse me, with the noise and so on, so.
Why
And the mass?
have we started the induction with n equals 1 and not 2?
Yeah. I start with the first. And what is the first? That I want to prove a property for all n in n star. Okay? Yes. N star here. Okay? So that's why I start from 1. If I have n equal to 0, n belongs to n, I start from n equal to 0. If I have a property n belongs to capital N minus 0, 1, I start from 2. Okay? So I start from the first. Okay? The smallest if you want. Okay. So I just write the sketch and after I will finish next session, but try to do at home, okay? So what I have to do now, I have initialized. I want to prove the heredity. So in fact, it's possible for me to write my reasoning. After I have to compute, and you will see that the computation are not that difficult, but not that easy, in fact, okay? But after it will be just computations, so techniques, okay? But for my reasoning, you need to have this in mind. So now, I start from 1, okay? I will suppose that it works for n, and I have to pass from n to n plus 1. So it's just a little picture to remind me what I have to do, to pass from n to n plus 1. What is the meaning of this one? I suppose that the property is true for n. So I suppose, I write it, a plus b to the power n is equal to the sum from k equal to 0 to n, c n k, a k, b n minus k. It will be my hypothesis, something that I am able to use hereafter. Hypothesis, okay? What I want to prove, so my job will be to prove what? My job will be to prove that I have exactly the same when I replace n by n plus 1. So what I want to prove is that a plus b to the power n plus 1 is equal to the sum from k equal to 0 to n plus 1, c n plus 1 k, a k, b n plus 1 minus k. It will be your job to do this. And of course, you are going to do this job using your hypothesis. Okay? So here you have written the reasoning you have to do. And after, okay, it's just computation. So computations that may be more or less difficult, I agree, but the reasoning here in some sense is finished after I compute and try to obtain what I want. Okay? It will just be after just technical skills, okay, a little of training to do, but the reasoning is this one. And I will conclude by the following. So, you have this one that you want to compute, and this one that you know. When you do an induction, you have to make the link between what you want and what you know. What is, in this particular case here, the link between what you want and what you know? In other words, what is the link between a plus b to the power n plus 1 and a plus b to the power n? Yeah, a basic relation, that is what we are going to use, that is a plus b to the power n plus 1 is equal to a plus b times a plus b to the power n. And what you have to do after is to do what? I use my hypothesis, I plug it inside, and then it's just computation that I will do quickly next session. Okay? But in fact, it's finished now. After, it's just technical skills. Okay? Try to do at home if you don't have done this exercise during the holidays or during the beginning of September, okay? And typically, okay, why I do it as an exercise now, okay, because it's something that will be used when I will define the binomial distribution, okay? So see you next week, okay?